Good morning, everyone, and thank you for joining us back here today. My name is Madison Deal, and I would like to welcome you all yet again to today's webinar, the third and final installment in our three-part series on hydrogen DRI, and steelmaking. Our goal for this webinar is to share the results of the HYBRIT pilot program and then demonstrate through modeling how the highly metallized zero carbon DRI that's been produced there can be efficiently melted in the EAF, unlocking the next step in steel decarbonization. And before we begin, I'd like to recognize the Decarbonization Subcommittee, our chair, Felix Furschbach of the Badishi Group, and our webinar chair, Joe Mori of Mori Consulting LLC, for all of their work and support in producing each of these webinars to advance the subcommittee's goal of educating the steel industry on sustainability and decarbonization. Two guidelines. Our antitrust guideline. This is a technical presentation that's focused on knowledge sharing, so please no discussions or questions relating to pricing or competitively sensitive information. And our anti-harassment policy. AIST is dedicated to keeping this and all of our events a safe and harassment-free environment for all parties involved. Couple webinar guidelines. Your audio as attendees has been disabled. So please submit all of your questions throughout the presentation using the Q&A function on Zoom, most likely found either on the bottom of your screen or in the More section. Some questions may be answered via the chat during the presentations, and others will be saved for a Q&A session once the presentations conclude. So please be sure to submit all your questions as they come to you. This presentation is being recorded and will be available on AIST's website, so no need to record on your own. And if there's any technical difficulties, please be sure to email training@aist.org. Now, without further ado, I would like to introduce the moderators for today. We have Megan Lansborough of Hatch. She's a process engineer specializing in hydrogen systems and industrial decarbonization, and David Marshall, a global consultant and founder of Performance Improvement Incorporated, as well as founder of the Decarbonization Subcommittee. Take it away.
Thank you, Madison, and thanks to you and Joe for leading this effort. I'd like to introduce Dr. Martin Pear, who's a senior advisor at SSAB and initiator of HYBRIT, a groundbreaking hydrogen-based steelmaking project. His title is SSAB's Transformation to Fossil-Free Steel with the HYBRIT Technology. His full description is on the screen. Martin, please take over.
Thank you very much, David. Good morning, everyone. First, I apologize for last week's problem with my connection. Hope this will work well today. Could you please share the slide? Let me see. I'm trying to just get to the page where I can see the slide. Sorry. Yes, I will start to make a very quick introduction of the reason why we started the HYBRIT development work in Sweden, and then share a few major milestones, what has been achieved the last few years, then end up with describing this transformation process that SSAB is currently carrying out in our company. So next slide, please. As we all are in the steel industry, we know very well that steel is extremely important material. It is essential for in principle, every important aspects of the modern society. It is also readily available everywhere, and it can be recycled again and again. And we know also that the need for steel in the future will continue to grow as more and more countries modernize. However, the current main technology that are used to produce steel from iron ore is essentially based on using coal and natural gas. And this emits a large amount of carbon dioxide into the atmosphere. So if we really want to make steel as part of the solution for the climate challenge, we need really to drive a technology shift. And the question is that possible? Do we have a solution for that? Next slide, please. So we, back in 2016, we started the HYBRIT initiative as a research project in Sweden. We teamed up with partners, a mining company and energy company, LKAB and Vattenfall. And we started to structure how we should run this research work. And we quite quickly wanted to study what is shown on this slide. To the left is the current blast furnace BOF production route, and to the right we want to illustrate whether we could repurpose the already commercially available natural gas-based DRI process using the shell furnace and go over to the electric arc furnace melting technology instead of the BOF. So the critical questions we were thinking that we need to get an answer is what would be the major differences in terms of the reduction using hydrogen, pure hydrogen instead of natural gas, both thermodynamically but also kinetically. How could control this process? The second question, of course, which is the key, is how to control or manage the energy balance in the shaft furnace, as we are quite familiar with how we run on natural gas, but we go over to hydrogen. What would be the possible solution to do that? And then the question regarding carbon. The carbon's role in the DRI became one of the central questions. Do we need to carburize the DRI before charging into the arc furnace? Or if we would need to do that, how can we do it? Then the next question we started to recognize in the development work is, do we have a solution to passivate the hydrogen-reduced DRI instead of, say, briquetting into HBI? This is mainly referring to earlier knowledge that hydrogen-reduced DRI are not stable in atmosphere. And we also encountered quite a number of occasions where this DRI, if not well handled, can start to burn. So that was one of the major questions we need to get an answer. Then moving on to how to optimize steel production. We know that currently a natural gas-based DRI, in many cases, if you have a cold location of the shaft furnace close to the melt shop, hot charging is one of the possible solutions to optimize energy consumption. And do we have this as the only solution, or do we have other solutions to optimize the energy efficiency in the whole system? Then finally, how can we integrate, say, hydrogen production using electrolysis with electricity grid that is increasingly having more and more share of renewables? If we integrate a hydrogen storage, what would be the best solution? Could the so-called line rock cavern technology be used? Because we use today to store natural gas, whether that could be also repurposed. So these were the key questions that we thought we need to get a clear answer before we can move ahead at large scale. Next slide, please. So now we started the research work. And next slide. And I share a few, say, major milestones. And these are, you have probably, most of you read about this in the past. One of the decisions we did from moving over from a project to really a big investment program is to create a joint venture company. So a joint venture company was created in 1 year after we launched the project in 2017. HYBRIT Development AB was established with the 3 owners. And we move ahead with a decision in our board and owners to invest in the pilot research program. And 2018 started construction of the HYBRIT pilot plant, which you see on this photo, and that was commissioned in 2020. So that was, of course, important. We could manage, even though we were in the COVID pandemic time. We could commission this shaft furnace facility, electrolyzers, and essentially we can run the research program at this pilot scale. 1 year later, we managed to produce successfully the first campaign where we could produce DRI using pure hydrogen. And with that, we decided also to showcase that this could also be successfully turned into steel. So we delivered plate products to one of our major customers, Volvo Group, who made this very nice truck you see on the right of this photo. This is an exciting product. Their future, say, fossil-free vehicle in 2022. Next slide. And 1 year later, we decided SSAB to also launch a product from our US facility in Iowa, where we could showcase that we can use 100% recycled scrap using renewable natural gas and biocarbon instead of fossil fuels, and could produce a steel with a Scope 1, Scope 2 emission below 50 kilo per ton of steel. So that's we branded into SSAB Zero. This is a very good complement of what we already showcased with the HYBRIT fossil-free products. And in 2025, last year, we could also certify that we can make steel with a certain percentage of hybrid DRI in this SSAB Zero product, make us possible to achieve the near zero emission steel standard that was launched by the First Movers Coalition, which is based on the International Energy Agency's guidelines. A good, important, say, a milestone for us to, as a company, to be able to make the big investment decisions. Next slide. Coming back to these were, say, these highlights we have done, showcasing our journey. But what is the most important is what has been done by the team at HYBRIT Development AB and the joint research program we have been running. And the aim of this is really to start from mining. Our partner mining company, LKB, has a clear ambition to decarbonize their whole operation, including the pelletizing plant and sintering process to make these pellets. That was an important step. And then, of course, the core part with our reaction with hydrogen integrated with electrolyzers and also the hydrogen storage. Then finally, the melting step in the electric furnace, whether this product can be successfully utilized. Next slide. Yes, the whole program is quite extensive. We built in some cases very large facilities, like the first photo here is at one of LKB's production facilities. establish a bio-oil facility replacing fossil oil, and that has been successful in the fuel shift. And this facility is then now under, say, normal use by LKB after we have finished this program. So essentially, it is possible to decarbonize the pellet sintering step. And then the major investment went to the shaft furnace and also electrolyzer plant, including the hydrogen storage. All of these are in Luleå at the SSAB's steel plant. And then finally, we utilize one of the existing pilot electric furnaces at Sverium, the research institute, formerly called MEFAS. And this has created a very good opportunity for us to test this technology, all these major steps. Next slide. Yeah, this pilot plant, of course, is the key part. And here we have put a lot of efforts. Big investment has been put into this facility, which is extremely flexible, and we can make various experiments, tests, and run campaigns in 24/7 for many weeks in this facility, study different setups, parameters, and configurations. Next slide. Yeah, this is just a photo of the electrolyzer plant. It's alkaline two-stack, 4.5 megawatts. And this has been also a lot of work that we make this functional and safe and deliver the hydrogen at the flow rate and the quality that we need to run the trials. Next slide. Yeah, this is just a principal photo showing the hydrogen storage. This is a line rock cavern, essentially a steel-lined storage underground, and that is encapsulated with concrete, reinforced concrete, with a lot of sensors, management, and so on. And on top of this storage, there is a hydrogen compressor station. So we compress hydrogen gas to 250 bars, and we can store hydrogen in this storage. This is integrated with the pilot plants. When we run, we can also utilize this storage. When we run the direct reduction campaigns, this becomes extremely valuable backup in case there is any disturbance in the electrolyzer plant. We can get constant hydrogen supply to the shaft. Good. Next slide, please. Yes, after more than 5 years of trial campaigns, we have finally concluded that using pure hydrogen replacing natural gas, we can now configure a rather simple flow sheet for the hybrid process, where we can choose to produce cold DRI directly from the shaft, or if we want, can discharge hot DRI and briquette it into HBI, or in case in the future, if hot charging is a preferred option, this is also possible to configure. So the technology today is run very smoothly at this pilot scale, and we have been running campaigns since 2020, and we are still running campaigns today. Continue to study this process, further refine the settings and so on. And we have developed a technology we call the regenerative cooling, which is protected by a patent application. So we can essentially recover all the sensible energy inside the shaft. So we essentially introduce cold hydrogen from lower part of the shaft, and this hydrogen gas cools the DRI on the way before discharge, and then this hydrogen gas joins the injected reduction gas at preheat temperatures. This is a very efficient solution, producing high quality cold DRI directly. Next slide. Yes, essentially in our future, say, industrial setup, we have concluded that this A highly metallized zero carbon DRI is the preferred intermediate product for us. And this is a product we have put a lot of efforts in understanding, studying various aspects of this DRI. And we are continuing to develop, modify the knowledge regarding this product. Next slide. A couple of major aspects, and this is slide shows that this carbon-free high metallized DRI has extremely high mechanical strength. It is much stronger than the iron ore pellets that is charged into the shaft. It is also much better mechanical strength to compare with HBI. Even so the highly metallized HBI does not have the same strength as this DRI, which is in a sense quite amazing. But we realize this, a lot of tests has been done. To the right, you see the job weight test that we've been carrying out at the HYBRIT pilot plant. It shows this very good results. Next slide, please. Yes, from the research perspective, we have now established significant, knowledge regarding how to run this process. We today have demonstrated that we can make steel using this technology, essentially eliminating all the fossil carbon dioxide emissions in the value chain from mining to steel. And the process settings are very well defined today. So we are quite confident this technology can be scaled up to a commercial scale. And the program has been run really in a very good way. We manage all of this development work within budget and essentially quicker than what we have expected in the beginning with the timeline that we planned for. And we have now quite a significant portfolio of patents that are now owned by the HYBRIT company. Okay, next slide, please. Yes, a very high-level conclusion. This is a most important slide, in my opinion. After these years of research and development work at this pilot scale, we can conclude that the hydrogen-based DRI that we can produce with HYBRIT technology, with very high metallization, normally higher than 99%, and having very high mechanical strength, chemically stable, and also with the regenerative cooling technology can be made with very high energy efficiency. And this is really the solution for us to move ahead, to change our production setup. And the hydrogen storage is also proven to be working very well. And it also provides significant benefits in electricity grid with the conditions in northern Sweden. So this makes us confident that we could essentially decouple iron making from steel making, and we can handle and store and ship this DRI and without losing energy efficiency. So this is an important conclusion we did at SSAB. Next slide, please. Yes, now just showing what is happening in our company. So next slide. Very quickly, for some of you who don't know SSAB, we are a steel company headquartered in Stockholm with around 9 million ton of steel production capacity. Next slide. Our major facilities, as I mentioned, we run two electric furnace mills in the U.S., one in Iowa, one in Alabama, where we produce heavy plate products. And in Nordic countries, we have a production facility in Sweden, Finland. These are mainly strip products. Even we have also two plate mills in the Nordic countries, one in Finland, one in Sweden. Three major sites with blast furnace operation, and this is where we are now making this investment to transform to fossil-free steelmaking. Next slide, please. So currently ongoing two investment projects. The first step in Oxelösund, which is this the smaller one, where we are currently in the final installation stage of this melt shop. The electric furnace melt shop, 200 metric ton tap weight. This is going to be commissioned the beginning of next year. Originally, this was planned to be commissioned within 2026, but due to some delays with the electricity grid connection, so this will be commissioned beginning of next year. And this is the first step. We will then shut down the blast furnace, coke oven plant, the BOF shop, go over to electric steel making. And the second project, which is the major one, is a new mill currently under construction in Luleå, where we currently run the largest blast furnace. And this is a 2.5 million metric ton of strip products, quite big investment, and that will be commissioned in 2029. We have the principal decision that we will also transform our Finnish operation in Roe. The decision is not yet done, but we have said that we will do a similar transformation as we did in Oxelösund. So we're working with this development decision. Hopefully will come in the future. Next slide. Yes, just the two photos showing these two big projects. I think I don't stop here. Next, please. Yeah, and this is, of course, very important that we have strategic customers that are engaged with this transformation, because this fossil-free steel, at least initially, will need to carry some premium in order to make the business case. We have currently more than 65 major customers that have entered into these strategic partnerships for our transformation. Next. Yes, I think this is the final slide I prepared. So we have been promoting what we call SSAB fossil-free steel based on this superior hybrid hydrogen DRI. And then we have the SSAB zero products, initially only using recycled scrap, gradually also introducing partly DRI, this hybrid DRI into this product. And really, we are moving ahead with these investments, and hopefully this will take us to the fossil-free steel that we have decided to turn the company to. So thank you very much for your attention. I'm happy to listen to Mike what would be the conclusion to use this product. Thank you.
Thank you very much, Dr. Pai. Okay, up next, we have Mike Grant presenting hydrogen-based DRI use in the EAF. Mike Grant is an independent consultant with nearly 40 years of experience in EAF and iron-making technologies. The rest of Mike's bio can be found on the screen. And with that, I will hand it off to you, Mike.
Well, thank you very much, Megan. It's a big honor for me to speak with you today and to follow the excellent presentation of Martin. I will share my screen. Can't forget to do that. 1 second. Did you see my screen?
Yeah, it looks good.
Okay, so the title of the talk is Hydrogen-Based DRI Use in the Electric Arc Furnace, and it's answered a question that's been discussed quite a bit in the steel community about the importance of DRI carbon content. And today I'm going to provide you a theoretical assessment, and this complements Martin's presentation on the production and use of zero carbon DRI. So hopefully this will make some suggestions that we can talk, that could be talked about later. You've all seen tables like this. The blast furnace is the big villain in today's society, producing 1.5 tons of CO2 per ton of steel produced. And this compares with 100% scrap-based electric arc furnace steelmaking, which is about 125 kilograms of CO2 per ton. These are direct emissions, emissions from the process itself. And we could look also over at the hydrogen-based DRI process with the EAF at around roughly the same amount of emissions. So both methods for producing steel reduce CO2 emissions by about 90%, scope one, and certainly these are the obvious choices for future steel making, low carbon steel making. Now, why do we use DRI? You know, people will say, well, scrap and 100% hydrogen-based DRI are similar. We all know that scrap contains impurities, and that we call them residuals. And the amount of residuals present in the scrap, if that melts into the steel, can limit the kind of steel that's being made. So, for example, for producing high-quality exposed auto sheet, the limitations for the amount of residuals that you can melt in is quite low. And therefore, given the types of scrap that's available on the market, quite often you have to dilute this scrap with ore-based metallics such as DRI or pig iron. And in fact, this is absolutely necessary when making exposed auto sheet. So in effect, we're using the DRI to dilute the tramp elements. Copper is the big one that we're trying to reduce. It can eliminate almost all your tramp elements if 100% DRI is used. Cheaper scrap can be used if we mix it with DRI, but in the end, we want to make high quality steel. And with decarbonization trending towards more and more EAF production, there's going to be a lot of competition for high quality scrap, and DRI is going to need to be available to replace that scrap that's being sought after. Pig iron, of course, is an ore-based metallic as well. That's currently widely used in the electric arc furnace. But again, that's made with a blast furnace with a high CO2 footprint. And since we're trying to reduce our CO2 emissions, pig iron will probably be phased out as well. Now, there are challenges with DRI, especially with low metallization. Martin mentioned 99% metallization for hydrogen-based DRI. Typical commodity-based DRI is around 94% metallization. Many of these DRIs have relatively low carbon content, so the yield and productivity of the electric arc furnace is reduced, whether using high metallized DRI or low metallized DRI. With the reduction in productivity, if you can build your DRI plant next to the EAF, hot charging is required to recover productivity. So I'm going to start with this diagram here. This is
all the power's up. Just check the light.
I'm sorry?
You're good, Mike. Keep going.
So we can't escape the fact that steel is an iron-carbon alloy. And so carbon is going to play a role in this picture no matter what. And if we look at the three main processes for producing steel, the electric arc furnace, the BOF, and the bottom blown OBM. These show that as we blow our carbon down, say to a low carbon content of 0.5 carbon, we are oxidizing quite a bit of our raw material, our scrap, our metallic iron. And you can see a typical 0.5 or carbon tap heat can put about 40% FeO in the slag. It's less for the BOF and even less for the bottom blowing because these two vessels mix the steel much more rigorously. And so there's not the gradients that you have in the electric arc furnace where all the energy is going in at the top. And so you're heating up the top with oxygen and you're heating up the top with the arc. And so there's very little convection that's taking place. So you have cold, high carbon steel at the bottom and very low, high oxygen steel at the top, coupled with a slag, which produces a high FeO slag, and this is yield loss. And why I'm showing this diagram, of course, because it plays into some of the assumptions I make later on. And these are, of course, all heats that I'm simulating assume 40% FeO content in the slag, 0.5 weight percent carbon tap. And each heat is 50% DRI, 50% scrap. We're charging exactly the same number of atoms at the beginning. We're charging that into the furnace, and we're tapping the exact same number of atoms when we tap. And we can do this in a theoretical exercise, but the purpose of that is to show the effect, of how we balance the carbon and the oxygen to maintain exactly the same yield. A theoretical exercise, but it's always good to know for evaluating these cases. All the DRI is cold, except for one example where we do a hot charging calculation just to show the benefits of hot charging. And I did not assume any biocarbon in these simulations. I only used fossil carbon. But even so, fossil carbon, the emissions aren't too high. Now, of course, if we look at this is the amount of material that you need to charge into the furnace to get 1,000 kilograms of steel out of the tap. And you can see, because, of course, a highly metallized DRI has much more metallic iron in it, much less oxygen. And so the weight of iron can be, that you charge, the total weight that you charge could be much lower compared to 94% metallized, where you have a lot of iron oxide, FeO, in the DRI product. In order to make up for that oxygen that you're containing in your DRI, you have to increase the weight of the charge. And this is a pretty simple principle. Of course, if we have a 2% carbon, as we're doing this comparison here, we see that the charge weight's even higher. So compared to the 100% scrap case. Now, all the calculations made were based on this reference of 100% scrap, about 395 kilowatt hours per ton of electrical energy consumption. And then you can see by all this diagram all of the different energies that are produced from the different reactions with oxygen and carbon. So we have burners, we have post-combustion, and then the bath reactions all contribute to the energy for the whole process. And the chemical energy actually makes up about 45% of the entire energy for the process. Electrical energy makes up the other half, but that's the one we always pay the most attention to. So this is the reference. And if we look at the different cases, comparing 0 carbon DRI with 2% carbon DRI, and we start with low metallization all the way up to high metallization, you can see obviously the the higher the metallization, the higher the metallization, the lower is the power consumption, or the higher the productivity of the electric arc furnace. Compare this with the 100% scrap case here. And if we look at the CO2 emissions, in fact, because we're charging less carbon in the process, we are producing less CO2, around 25 to 45% lower CO2 emissions when we charge zero carbon DRI. So there's that benefit alone, despite the fact that you're consuming a little bit more energy and you don't have carbon in your process. Now, natural gas-based DRI puts carbon in the DRI, which theoretically shows it has benefits, but in reality, natural gas-based DRI is very difficult or expensive to go much above 96% metallization. As Martin explained, 99% metallization is very achievable with hydrogen-based DRI. So really, when we're comparing carbon-based DRI with hydrogen-based DRI, you compare 99% with 96%, and you can see here that theoretically there's about a 5 kilowatt hour per time difference. And this falls well within the normal heat-to-heat variability. So essentially, this small difference you might not even notice when you're comparing the two. If you are able to hot charge your DRI, we can go to 600 degrees C. We can bring that electrical power consumption down to the equivalent to that we had for the reference case with scrap, and this will recover all of the productivity lost through the use of DRI in the system. So in reality, the zero carbon DRI with high metallization is effectively as good as 96% metallized DRI with 2% carbon. So, of course, there's been a big debate on the importance of carbon in DRI. Keep in mind that the carbon in DRI comes in the form of iron carbide, and iron carbide doesn't melt. And so it dissolves, and so that from a melting point to a perspective, it doesn't really help so much. The secret is to charge the DRI continuously in a rate that it could effectively be melted by the arc. The carbon, of course, improves the yield. It makes the slag foam better, and the reason for that is because essentially it diminishes the need for extra control with your carbon and oxygen balance. So in effect, if you're putting carbon in the DRI, you don't need to charge as much carbon or inject as much foamy slag carbon. Keep in mind, though, that injection carbon in traditional conventional systems is about 50% efficient. We lose about 50% in the fourth hole due to the negative pressure inside the electric arc furnace. It drags a lot of the injection carbon out, and we lose a lot of that. But with a higher metallized zero carbon DRI, we need to have a carbon injection system that is well controlled and high efficiency. So 50% efficient, as in the traditional carbon injection systems, is not good enough. We need to go higher. And the amount of carbon, of course, depends on the metallization of the DRI that you're charging. So I've calculated the amount of carbon that needs to be charged in each case, depending on the metallization. And you see with 94 percent metallization, we need about 25 kilograms of carbon per ton of steel just to control the FeO in the slag, reduce that FeO back to iron so that we can recover that metal. And of course, these are emissions. And as we increase the quality of the DRI, we approach 99% metallization. The amount of carbon that we need to inject comes down a lot because we need to reduce a lot less FeO. One problem about with such low carbon injection rates is pretty hard to control. Practically, it's pretty hard to control the injection rate of carbon at this low consumption value. And given the fact that with a conventional carbon injection system, you're losing 50%. So it's really hard to know what you're putting into the process anyway. But this is going to be a topic that needs to be dealt with as we approach, as we move towards more hydrogen-based DRI. There are companies now working on improving the efficiency. Talman Technologies is an example. They use a supersonic shroud to kind of encase the stream, and they've gone from about 40%, 40 to 60% efficient up to about 95 or greater. And this even helps for biocarbon injection. Biocarbon being notoriously very bad, low density, very hard to inject it. You lose a lot more in the fourth-hole. Apparently, this also works very well with biochar. So there are companies out there working on this. The more efficient you have, the more you can control it, the more you know how much carbon you're putting in the system, and you can balance that with oxygen. So just to wrap up, hydrogen-based DRI, and we demonstrate, at least on the theoretical level, it's effectively the same as high carbon 96% metallized DRI. And the question is how do we control the carbon and how do we control the oxygen so that we don't lose too much of our iron in the form of FeO. And really, I think up till now, carbon injection is more of an afterthought in most EAF operations. It's not considered to be an essential tool. So what happens is, the carbon injection is judged based on whether the slag foams or not. And in fact, really, if you can control the FeO content in your slag, you can control the foaming. And this means precise control of carbon injection and oxygen injection to balance. And with that, I think that concludes my presentation. Thank you very much. It's a pleasure talking to you.
Amazing. Thank you so much, Mike. Okay, and now I think we're going to move into our Q&A portion of our webinar today. Dr. Pei, oh, amazing. Okay, great. Okay, so some of the questions that have been posted in the chat. The first one here is for Dr. Pei. How many times reducing gas is recycled before leaving the unit?
Oh, yeah. Essentially the top gas from the shaft is recovered fully. We cool it down, separate the dust and this hydrogen after separation from water vapor goes back to the circuit. So I think maybe it's difficult to say how many times. We need to control as I mentioned, one of the key technologies we have developed is the heat balance in the shaft. So essentially, in the recycling circuit is the gas preheater. So this gas is preheated to the desired temperature as to be injected into the shaft again as the reduction gas. So that circuit is functioning in that way. So the only thing we need to take care of is a small portion of top gas that need to be bleed off. That is driven by the need to control the nitrogen content in the shaft, because we use nitrogen gas as a sealing gas for the valves and so on and so on. So we don't have a bleed off, small stream bleed off gas, nitrogen will accumulate. So essentially everything is recycled, and the consumption corresponds to the stoichiometric need for reduction. So in this way, I hope that I can have explained this. The hydrogen reduced reduction process is extremely efficient in terms of utilization of hydrogen.
Perfect. Thank you. The next question here is, can you comment on the hydrogen utilization and the leak rate?
Sorry, can you repeat? In a hydrogen?
The utilization and the leak rate.
Under?
Leak rate, the leak rate, if any.
Okay. Yes, as I mentioned that we need to control the nitrogen content in the shaft, since we use nitrogen as a sealing gas for all the charging valves and discharging valves and so on. So it's a very small percentage that this bleed off need to be taken care of. So, and that can be exported as an external fuel, for example. So I should say that the hydrogen utilization for reduction is extremely high.
Perfect. The next question that we have for you is, one would expect that metallic iron with no carbon will melt at higher temperatures. What enables HYBRIT DRI to melt easily in the electric furnace? Is it the porosity?
Essentially, that's why we prefer to make it in the form of DRI. So the size of the DRI is much smaller than HBI, and density is lower. So when we control the feeding of this DRI into the electric arc furnace, it melts quite nicely, much easier to control compared with HBI. We have experienced. We made a lot of trials in the experimental electric arc furnace at the Sveri, and we now know how to really control the process parameters. So another advantage with this HYBRIT DRI compared with HBI is that when you make HBI, normally you get the moisture in the HBI, which can be avoided if we make this DRI. So that is also additional advantage in the melting step.
Amazing, thank you. This one I'm going to open to both of you. What is the next expected scale of HYBRIT DRI plant?
Yeah, if I could, we are planning as the first step of scale up. It's a unit producing 1.35 million metric ton of this DRI per year, and that is currently under development.
Awesome, perfect. The next one here that I have is for the same target iron oxide content in the EAF slag. how can the CO2 emissions be compared between using carbon from the metallic charge and using injected carbon?
The efficiency of the carbon is very important, of course. If the carbon is in the DRI and it charged at the correct rate, so it melts as soon as it's charged, you can virtually have close to 100% efficiency of the carbon that you're putting into the system. So the quantity of carbon would be quite low for a given carbon content in the bath. With carbon injection systems, traditional carbon injections, it's essentially a pipe they put in the wall of the furnace and they blow it in and hope it gets into the slag. Well, typically you lose about 50%. And so that 50% goes out the fourth hole, it gets into the dropout box and starts to smolder, makes CO2, and doesn't provide any heat. And so obviously it's more efficient in today's technology to have carbon in the DRI, but then again, the technology for carbon injection needs to be improved significantly if universal low carbon DRI is going to be used in the future.
Perfect. Thank you. Mike, I think another question for you here. In your steelmaking process, how much injection carbon have you had to use? Is this fossil carbon or biocarbon?
Well, I mean, you saw the lower the metal, the higher the metallization, the lower the required carbon, because you need that carbon to fight the FeO that's in the DRI. So the more metallization we have, the less carbon we need. But in all my calculations, I assume fossil carbon. So we could get with the zero carbon DRI, we could get our CO2 emissions down around 40 or 50 kilograms per ton of steel. And those emissions coming mainly from the injection carbon and the electrodes.
Perfect. Thank you. We still have a couple questions coming in here. I think this will probably be our last one, but Mike, so the comment here is interesting calculations showing that the high carbon DRI, natural gas base, and no carbon DRI, hydrogen based, will perform similarly in the EAF. Would then the cost of producing steel pretty much depend on cost difference between the two forms of DRI, and / are there any other factors?
Yeah, I mean, essentially that would be the cost difference. You keep in mind that there's probably going to be some sort of incentive or penalty for emitting CO2, and those need to be included in the cost. But yes, cost is what makes the world go round.
Perfect. Thank you both so much. I know there's still lots of questions coming in, but to our audience, you can see that they have their emails up on the screen. So please email them to follow up. Thank you very much to the audience, and I will pass it back to Madison.
Thank you. And thank you, Mike. Thank you, Dr. Pei, for your work in the presentations that you put together for our attendees today. We hope you learned something new that you can take to make wherever you work a better place. So just a reminder for webinars, these are all recorded and posted on AIST's website. So you can go back through, we have our part 2, if you missed that, of the hydrogen production posted, as well as our introduction to sustainable steelmaking, which is a really great overview of what it takes to be sustainable and what it looks like in today's markets. That can be found either in the conferences and expositions tab or under the technology committees tab on our website. And just real quick, some upcoming technology trainings and events for everybody to get excited for. We have our 32nd annual AIST Crane Symposium, Global Steel Dynamics Forum, Women in Steel, Sheet Processing and Finishing Lines in the fall. And then specifically related to sustainability, our Energy and Utilities Technology Committee will be putting on the Energy Reduction in the Steel Industry training seminar to take place in Cleveland. And don't forget, we are just a month away from AIS Tech, so we really hope to see you all there. Thank you all again so much for your attention, your attendance, and thank you to our moderators, our presenters, and the Decarbonization Subcommittee. Hope you have a great rest of your day. Thank you again.
Thank you.